Hi guys, today's video is on 6.1 to 6.2 compound and continuous interest. So far we've learned about annual interest in 6.1a, where your principal grows or decays by a given rate annually. And this model follows the formula a equals p times 1 plus r to the t power. And it's accurate for many models, but putting money into a savings account or credit cards follows a different interest model called compound interest. Compound interest is getting interest on your interest. Okay, and I'm going to use this example here to prove it to you. So compounding is like how often you calculate something. And so banks will actually compound more than once a year at the end of the year. If you have, like, say, an interest rate of 12%, this is not true or never will happen, okay? But if you did, then every month you would get 1%, right? I divide it by 12 and get 1% per month. And then if I put $100 into a savings account, then I can compound that 100 12 times a year. So how much is it? Well, 1% of $100 is just $1, right? So we're taking $1 and we're adding this. So we have 101 after 1 month. And so the next month we'll have 102, 103, 104, all the way down to December, we'll have $112. No sense. Okay, so what compound interest does is when your bank calculates after this month, it doesn't pay you out. Like, they don't give you a check to cash out your dollar, right? They just drop the dollar into your bank account. So when you calculate your next month's interest, now you're going to have 102.01. And I'll prove it to you. We'll do it here. Ready? You're taking your 101 times 1.01. Now, it doesn't seem like very much, but let's keep going. Times 1.01. Right? So then we take our 102.01 cents, and we have an extra cent now, and we're going to multiply it by 1.01. Excuse me, 103.03. Okay, and I'm going to keep going. I'm going to take that amount and multiply it, right? And multiply and multiply. And you'll see that by the 6th month, it's not just 1 cent or 2 cents extra. Now we have 15 cents extra. So let's write that down in June. We have 106 and 15 cents. And if I keep going all the way to December, which is 112, I have 68 extra cents, which off of $100, it doesn't seem like very much. But you guys remember that as we grow exponentially, 13, 14, 15, you see how, like, now it's $1 more, 16, 17, 18, and like, right? So now we're in like way higher numbers. Like, this is only month 20, I think, but we have $4 extra in month 20. So after 2 years, seems like a really slow grow. But if we added some zeros and we said this is $112,000, right, compared to $112,680, that's not a bad thing to take $680 just by leaving your money in the bank, right? So rather than doing this all on your calculator, there's got to be an easier way, which is our formula of A equals, starts off the same way. You have 1, right? And then we're going to add because interest is always adding. But we took our rate and we divided it by 12 this time because I calculated it 12 times. Well, it's not always 12. It's whatever we decide to calculate, right? So N is the number of times compounded per year. P was still principal, or your starting value. R is your rate in decimals. Quick reminder that it's your percent divided by 100. And then T is your time in years. So let's take a moment and just define, like, how many times each of these is. So monthly we said was 12 times a year. Quarterly is 4 times. Semi-annual is 2 times, and annual is 1. how many weeks are there in a year? That's 52. And then 365 days in a year. So I'm going to copy this formula down on the next page just so that we can have it there. And all we're doing is plugging numbers into this formula. A equals P 1 plus R over N to the... Oh, and I forgot. I'm so sorry. We need an exponent. Yikes. That would have been bad. So my exponent used to be just T, but now since we divided by the number of times we're compounding, we need to multiply it back. So now we're not just compounding like one time a year for 1 year, it's 12 times 1 or 12 times 2, right? For a total of more times. And the number of times we multiply is what our exponent is. Okay, sorry about that. So let's deposit 9,000 in a bank account that pays 2%. So let's see, 9,000, 2% interest increasing 3 years, compounded monthly. So this is P, this is R, but R equals to 2 divided by 100, which is 0.02. This is T, and then monthly is N equals 12. So let's type this all in. Ready? We got A equals 9,000, 1 plus 0.02 over 12, and then we see 12 again, always, okay, times 3. Now, on your test, you would have to write this and then write out your calculator answer that you get over here, which is going to be, let's see, I'll type it out, 9,000, 1 plus 0.02 divided by 12 to the power of, and you need parentheses. Okay, so the most important thing that people forget is that second parentheses for the exponent. So let me write this out in red. On your calculator, you should have 9,000, 1 plus 0.202, sorry about that, divided by 12. You don't need parentheses around the division problem, but you need parentheses about 12 times 3. Okay. And that equals to 9556. And since it's money, I'm going to round to the nearest cent. So on a test, you need the 2 parts in blue. This is just for reference right now. Okay. So I want you to pause the video now and try the next 2 problems and see if you get the same answer that I'm going to get in just a moment. Okay, so you'll notice here that these 2 numbers are not significantly higher than what you start with. So if you get something like 30,000 from 3,000, something went wrong. It's not going to grow like crazy, because it's not doubling. It's just like part of what you get, right? But check and make sure that you've got your answers correct. If you aren't able to get the right answer on your calculator, please let me know in class how I can help you, or like that you're having trouble, and we can go over it and find your mistake. So our last section, this is actually 6.2 now, is about this special number. It's called the natural base, and it's a natural base of e. But in math, we have special numbers such as pi, which is 3.14, but it continues forever, and imaginary number of I equals square root of -1. And how these numbers come into play is that someone spends a really long time finding a pattern that always works, and they use it so that they don't have to calculate or measure everything over and over, right? So like pi is used for circumference, and so people got tired of like measuring around a wheel every single time. They said there had to be a faster way to get the circumference or the distance around the wheel, and so they calculated for pi. Someone found a pattern for e, which follows this right here, where you're adding over and over, but the number you're adding by gets smaller and smaller because the denominator gets bigger and bigger. And as this happens, the number you approach is 2.718. And it goes forever just like pi. You can treat e like a variable, like pi, like 3 pi or 3e, or you can treat it as a number and multiply 3 times 2.718. On your calculator, 2.718 shows up as a variable right here, right underneath pi. Do you guys see the division symbol? You can go second e, and that gives you the number. Okay, so it's pre-programmed into your calculator. And so what that means is, since this is just a number, we can actually graph e to the x and have that in our table of values as just 2.718, right? Because e to the 1 power is just that number. And then I could take this squared and get e squared on my calculator and get 7.39, right? And so you can graph this knowing that, well, that's just a little bit under, okay? Anything to the 1 power is, or anything to the 0 power is 1. So I just wanted to show you guys that this is still a graphable function, okay? Because e is a number. So what are we doing with all of this? Well, when interest is compounding continuously, let's say I told you to plug in n equals to like 1 billion, what happens is that the number that you get, ignoring everything else, so like if I had you plug in like something over 1 billion to the billion times 4, right? And if I ignore this, and what happens is sorry, let me take a moment. What happens is that everything in this section approaches e. And so we can now have a new formula, which is a equals p times e to the rt power. So the only difference is rate has been bumped up now. Okay, and e is a number. This happens in two situations: when population grows and decays, and when you are continuously compounding interest. The second one is really easy to pick the correct formula because I literally have to write your interest is compounded continuously. The one on the test that gets people is population growth and decay. I'm not going to make this explicitly clear that we're using E, but you can think about it like when we're having kids and like people are being born and dying, no one waits for the end of the day to calculate how many people are born or dying, right? Or like calculate the rate. So we need to then just assume that population is continuously changing. And so that's why population growth is automatically E. So how do we use this in a formula? Same thing. I do want to talk about how I give you a formula, but I also give you all this extra stuff to confuse you. All you need is, it's currently 48.5, right? Which is our initial. It declines, I always miss this every year, at 2.5%. Okay, that means this is my 0.025. Okay. And then after 25 years. So we're going to plug things in just like we did before. And we assume that we have, starting with 48,500, we have no 1 plus. It's a population problem. So now we're going to use e to the power of negative 0.025 because it's declining. And then times 25. And so how do we put this into our calculator? You'll literally go 48,500 e to the power of negative 0.025 times 25. This is my calc. And you should get approximately 25,960 people. I rounded to the nearest whole number because people cannot be decimals. Okay. This last one is the same idea. Anytime you're given a formula, you don't need to freak out that you don't understand it. Like, even if you don't understand where the formula came from, you can still use it and solve for unknown variables. So if your parents will need 25,000 in 10 years to pay for your brother's college tuition, and they invest at 9.8. Notice I skipped all the extra words. But it's saying, how much should your parents invest today? Now, today must mean the starting value, right? So we don't know the starting value, which means that we have an unknown P. I do know eventually I want to end at 25,000. We know it's continuous. Oh, I should underline that. That's important. In time. Since it's continuous, we're going to use the E formula, and our rate is 0.098 times 10 years. Okay, so oftentimes students see this and panic, but remember that all of this is a number. P is what we want to know, right? Or what we want to solve for. So we want to get P by itself, and if we're multiplying by just a number, I can undo by dividing by e to the 0.098 times 10. And what I divide on one side, I must divide on the other. And this cancels out. So now I have P equals, I'm just going to flip the sides, 25,000 divided by e to the 0.098 times 10. And you can type that directly into your calculator, no extra parentheses except for this part. So I'll write it again just in case. So you'll, in your calculator, right? And then you're going to get a number out. Let me just type that in. Divided by e to the power of 0.098 times 10. And you get P equals, or your principal that you should put in now, is 9,382.78 cents. And that money will grow in 10 years at a rate of 9.8, as long as you don't touch it, into $25,000, which is pretty sweet. That concludes today's lesson. Let me know if you have any questions.